Hey, it's Jim, and this is level 1 of the CFA program, the topic on quantitative methods and the learning module on probability mathematics. I sure hope you love as much as I do the Institute's decision to chop these level 1 readings into what they're now calling learning modules. And it really is advantageous for us now that we get into, the 4th and 5th and the 6th learning module here in the very beginning of the CFA program. What this allows us to do is to consume smaller pieces and smaller packets of the curriculum so we can focus on these things, and then they become a great foundation of knowledge so that we can apply that later on in level 1 and then of course in level 2 and in level 3. Now, you might say to yourself when you look at these LOSs here, you might say, especially the first one, hey Jim, haven't we done this before? Expected value, variance, and standard deviation. And of course we have. We've spent a lot of good time calculating average and standard deviation under a variety of scenarios. But now this learning module is focused on portfolio returns. This is what we know. As good investors, we're not going to take all of our capital or all of our clients' capital and invest it in just one or a handful of financial securities. We're going to diversify. We're going to have a portfolio of securities. So it makes perfect sense then to say, okay, we have these individual means and standard deviations for all of our securities inside of our portfolio. What is the overall portfolio return? So look at the key words in these LOSs. The first one, portfolio returns. The second one, portfolio returns. The third one, optimal portfolio. So think about, we're going to apply at the individual level, now at the portfolio level. So let's start with super simple idea, the expected return of a portfolio. Once again, the expected return of a portfolio is the first moment of the portfolio's distribution, and it's just the average, and you've done this multiple times. It is simply a weighted average of the expected returns. And there's a good equation in that gray box. You'll have to use this, I'm going to say 100 times before you end up passing level 3. We're just going to take the weight in an individual security multiplied by the return on that security. There's the W1 and the R1, and then we're just going to add however many securities we have in the portfolio. Now we'll work through an example with just 2 of them here in the next couple of minutes, but you could have 5 or 10 or 100. I tell you, if the Institute gives you 100 stock portfolio and asks you to compute the expected return, just pick C and move on with your life. Of course, it's not going to ask you to do that, but it might ask you to do the expected return on a 2, maybe a 3, maybe even a 4 asset portfolio. And so you can just apply that equation. It should be pretty simple. Now, before I go to the next slide, you might be tempted to say, all right, Jim, we just did expected value. We're going to do variance. And the equation is going to look identical to what we have in that gray box. We're going to take weight 1, and we're going to multiply it by the variance of asset 1, then weight 2, multiply by the variance, and so on and so forth. Well, you would only be half right. So that's the beginning of the equation for the variance of a portfolio. But let me warn you, and let me give you an example. Ready? Let's suppose we have 2 assets. And let's just further suppose, for simple math's sakes, that we have 50% in each asset. During the first week, asset 1 goes up by 10%. During the first week, asset 2 goes down by 10%. So what has happened to the value of our portfolio? Well, it stays the same. That must mean that there's no risk, right? Well, how do we incorporate the way that the 2 assets move against each other or move with each other? So we need a new concept. So notice up at the top, we've done expected value, we've done variances, we've done standard deviation, but we need to have a conversation on covariances and correlation coefficients. This is an extra statistical term that is super critical for the analysis of portfolios and a bunch of other things that we'll do inside of the CFA program. So I want you to think about this. Covariance and correlation coefficient, these are measures of the direction and the magnitude of a relationship between variables, like the movement of 2 shares of stock. What could happen? You could have a company like Walmart and a company like Target. What are their covariances and correlation coefficients? Well, when one goes up, the other one probably goes up, and probably by similar amounts. So the covariance is going to be positive and strong between Walmart and Target because they're direct competitors, they're in the same market, they have essentially the same target audience, etc., etc. Now, there'll of course be differences inside of those two companies, and we'll learn about those differences throughout the program. But then take a company like Walmart and then take a company like ExxonMobil. Oh boy, when Walmart goes up by 10%, what is ExxonMobil going to do? Is that return even related to what happens in Walmart? Well, probably a little bit. That relationship is probably positive, but it's probably not very strong. All right, so let me repeat. Covariance and correlation, they're a measure of the strength and direction of a relationship. So the question then becomes, when I hit this down button here and go to the next slide, how does all that stuff get incorporated into the standard deviation of a portfolio? Well, here we go. So notice what the top is. We're solving for, on the left-hand side of the equal sign, we're solving for the variance of the return on a portfolio. And here we're going to simplify things by just looking at two assets, asset 1 and asset 2. So what are we going to do? We're going to take the weight in asset 1 and we're going to multiply it by the variance of returns in asset 1. And then we're going to add that, the weight in asset 2, and multiply that by the variance in asset 2. So that top part looks an awful lot like this thing right here. But what's the big difference? Notice that we're using variances, so we might as well square the weight term as well. So there's the big difference. Make sure that when you compute the variance of a 2 or 3 asset portfolio, you square the weight and then you use the variance, or you square the standard deviation. Now, at this point, I'm going to just ask you to trust me and to trust the Institute's learning module. Sooner or later in the program, I'll have a really good explanation of why there's a squared term there for the weight. But for now, let's just pause and let's put our trust in the Institute that we're not just making stuff up. Has to do with the derivation of a portfolio variance. And when you take the difference and you square them and you do all sorts of stuff in calculus, then you get a squared term. But then notice that we have a plus sign down at the bottom. We're going to add the weight in 1 and the weight in 2. So we're going to multiply those weights. And then we're going to multiply by a measure of the degree and magnitude and direction of the relationship between stock 1 and stock 2. We're going to call that covariance here in this equation. We're going to put a 2 there because asset 1 varies with asset 2. And asset 2 varies with asset 1, so we have to count it twice. Now let me go ahead and extend this to a 3-asset portfolio. So think about this. If we have 3 assets, that top equation is, the top part of the equation is going to be identical, but we're going to have a plus sign out there. We're going to have weight 3 squared times the variance of 3 squared. You got that? But then at the bottom, we're going to have a plus sign. We're going to say plus 2 times weight 1, weight 3, covariance between 1 and 3, and then plus weight 2, weight 2, weight 3, and the covariance of 2 and 3. So as you add assets to the portfolio, you add tons and tons of covariance terms. It gets a little bit more complex. Now, the good news for you guys is that if you look at the at this module and you look at the problem at the end of this learning module, it's just 2 assets. So let's, for now, focus on 2 assets, and maybe later we'll do 3 and 4 assets. So let's go ahead and work through a quick example here. We have 2 mutual funds, A and B, 60% in A, 40% in B. There's a covariance term of 0.0144. There we have a 15% return on A, 10% return on B, standard deviation. So notice, and let me go back here real quick, that the Institute is going to ask you to compute the standard deviation of a portfolio, but it's going to give you as inputs all of these variables. So there they are in the table. And the question is, what is the portfolio's expected return and standard deviation of returns? Well, this may sound like a daunting task initially, but I promise you, by the time we get to the end of level 1, you're going to be able to do it like this. All right, so the expected return, this is super easy. What are we doing? We're taking 60% of 15, and we're going to add 40% of 10. So there's our expected return of the portfolio, 13%. Well, now we need to know, how wrong could we be? Remember in a previous learning module, I called it the degree of error. Well, let's do the portfolio variance. We're going to take 60% squared, don't forget to square it, times 20% squared, there's the variance. 40% squared times 15% squared, there's the variance of asset B. And then we're going to do 2 times 60% times 40% times that covariance term there. You get, what is that, about 2.5, take the square root, and you get about almost 16%. So think about what this means. Calculate and interpret. So we computed the expected return, 13%. We computed the portfolio standard deviation, which is about 16%. How do we interpret that portfolio standard deviation? That's a measure of the riskiness of the portfolio. It measures how wrong we can be. We're expecting to get 13% out of this portfolio, but we're going to be wrong on average by about 16%. Now that's 16% of the 13%. So wow, we can go up and down. So you get the sense, and I've said this in previous learning modules, and I think it's worth repeating, that higher standard deviations mean higher risk. Suppose that portfolio standard deviation, for some crazy reason, turned out to be 100%. We expect to get 13%, but our standard deviation is 100%. Well, really, we have no idea what we're going to get out of this portfolio. High standard deviations mean high uncertainties, almost anarchy out there, right? We're just floating in the waves of the floor of the New York Stock Exchange. And with a standard deviation of 100%, we pretty much have no idea what's going to happen in the future. Now, keep in mind, I'll give you a little hint here. Sooner or later, we're going to have a conversation on what is the standard deviation of individual securities. The average is about 45 or 50%. The average standard deviation of the S&P 500 index is about that number right there, about 15 or 16 or 17%. So we can manage this risk. Sooner or later, we're going to say, okay, we've computed these things. How do we manage them? Oh man, that's going to be so cool when we start talking about the policy statement for our clients. Now, notice in that last example, we were just so kind to give you the covariance. Well, what if the Institute asks you to calculate the covariance? Well, you compute the covariance in the exact same way that you compute the variance of an individual stock, but instead of squaring it, you multiply it by what's going on with the other stock. Hopefully that makes perfect sense when you look at that gray box. Covariance between X and Y is the difference between each individual X and its mean value times each individual Y and its mean value. So remember, when we did variance, we took X minus the expectations of X and we squared it. Well, now we're getting our eraser out and we're erasing the superscript 2 and we're multiplying it by that other variable. So look at the example we have up in the block there. For instance, we could be interested in the degree of co-movement, co-riskiness between interest rates and inflation. Well, what do? We get a sample of interest rates. We get a sample of inflation. We compute their mean value, right? And then we go through and do the same thing that we did for variance. And there's the covariance term. Now, when we're doing the sample covariance, we're going to sum all of those differences. There's xy minus x bar, right? Inflation. And then there's yi minus y bar. There are interest rates. And then because this is a sample, and we'll learn about this in an extended manner when we do more detailed quantitative methods conversations, we're going to divide by degrees of freedom or n minus 1. Not divide by n. We're going to divide by n minus 1. Now, here's a summary page of what I've been saying here all along. What is the interpretation of covariance? Returns on both assets tend to be on the same side of their expected values and a positive relationship between returns. Negative is just the opposite. Zero covariance mean the assets are unrelated. When one asset goes up by 10%, the other asset, it could go up by 10%, it could go up by 5%, it could go down by 5%, it could go down by 27%, it could go up or down. We have no idea. There's no relationship. That's what a zero covariance means. Now remember, this covariance is over that sample period. So you can't say if one stock goes up by 10% and there's a strong positive covariance between the two, that the other stock on that same day is going to go up by 10%, right? know that this is over time so that on average, you're going to get that strong and positive relationship. Now, what the Institute does in this next part of the learning module is it turns itself into a statistics textbook, and it gives you what is known as the variance covariance matrix. And it begins with just the covariance matrix. So look, we've got three assets, A, B, and C, going down the left column. We have three assets, A, B, and C. Did I say D? Three assets, A, B, and C, going down the left column. Three assets, those same A, B, and C, going across that top row. And what we're going to do is we're going to put the covariance term in there. And so this is a good indication of why we had to put a 2 in that equation back just a few slides ago. So look at A and B. Let's skip down. So what is that? That's the covariance between B and A. And then over at the top right in the middle, there's the covariance between A and B. So there's 2 of them, so we have to count it twice. Now look at the diagonals. The covariance between A and A, and the covariance between B and B, and the covariance between C and C. Well, that's another way of writing the variance term, which is why this is referred to the variance. The variances will be on the diagonals, and the covariances will be in the off diagonals. So this is known as the variance covariance matrix. There you go. There's sigma squared there, the variance terms, and then there are all the covariance terms. Now, remember when we gave you that example for the covariance term? Let me go back and see if I can remember what it was. What was it? 0144. There we go. 0144. Here's my question. Can you interpret that 0144? What does it mean? And the reality of life is that the covariance term is very difficult to interpret by itself. In fact, the range for covariance is from a minus infinity all the way to 0, and then all the way to a positive infinity. Now, of course, we really don't have positive infinity or negative infinities in covariance calculations, but some numbers could be really high. I mean, suppose that you calculated the covariance between the wait time for money machine and the dividend yield on the floor of the New York Stock Exchange. And suppose that came out to be, I don't know, a minus 59. How do you interpret that minus 59? Well, that covariance, that's probably 0, but I made up that number here between those two variables. So what we need to do is we need to take out a little tool in our quantitative methods handbook. And econometricians do this all the time. When you have, can you see my hands out here? I hope you can. When you have a random variable, when you have a statistic from 2 random variables like covariance that has this wide of a range, what you can do is you can put those things into a vise and squeeze it all the way down. You can squeeze it so that it is easily interpreted. So what statisticians do all the time is they standardize a random variable. And to standardize a random variable, you simply just divide it by its standard deviation. When you have covariance, what you do is you divide it by the product of the 2 standard deviations. We're standardizing this thing. So instead of a range from a minus infinity to a positive infinity, with covariance, now we have correlation coefficient, which has a range of a -1 to +1. Now we can wrap our hands, we can squeeze that correlation coefficient, and we can come up with a really, really good interpretation. What did I say earlier? We have no idea what a 59 covariance means. But if I told you that the correlation coefficient between Walmart and Target is 0.9, oh boy, now we have something. Now we can say, hey, when Walmart goes up by 10%, Target is going to go up by 9%, right? 90% of that 10%. Target is going to go up by 9% on average over that sample time period. Not every single day, but on average. So what does a positive 0.9 correlation coefficient mean? It means it's positive and it's super strong. Oh, wow. So there's the equation there in the gray box to get the correlation coefficient. And notice that there's a little sideways p there. That's a rho. That's the standard notation for correlation coefficient. All we're going to do is take the covariance and divide it by the product of the two standard deviations. This magically, how about if I say statistically, puts it in a vise and squeezes it down to -1 to +1. So there we go. Here's a summary page of my little crazy example with my arms going way out. And the vise, I think it's really, really good visualization to remember whenever you standardize something, you're bringing it into a narrow range. We'll learn about standardization multiple times. All right, here's a super simple example here. Notice the question. Calculate and interpret the correlation between an interest rate and inflation. So what have we done? There's the covariance. There it is, -0.00075. Standard deviation of one is 5.5. Standard deviation of the other is 12. So what are we going to have to do? We're going to have to calculate that correlation coefficient. Just take the 75, divide by 5.5 times 12. And you get the -114. So what do we say? The first interpretation is the direction. So they are negatively correlated with each other, which means when one goes up, the other one tends to go down over time, right? Not on a daily basis or a weekly basis, but over time. And the fact that that 114 is pretty close to 0. I mean, it's not exactly 0, but this indicates a weak relationship. So it's negative and weak compared to my Walmart and Target example, which was positive and strong. Let's go ahead and extend our conversation on covariances to what we did in a previous learning module where we threw probabilities in there. So the question then becomes, suppose that we have probabilities of these events. Maybe these are random variables, X and Y. Maybe they're stock returns. They're probably going to be stock returns, but they could be almost anything. How do we incorporate probabilities? And in fact, because we have two different stocks, we need to have this thing called a joint probability. So you might imagine that the covariance term can include probabilities. So look in the gray box there. What do we have? We have an xi minus x bar. We've seen that before. Then we have a yj minus y bar. We've seen that before. We know those are the critical components of computing the covariance term. But then squeeze over next to the two sigma signs, we have probabilities. So we're going to ask ourselves the question, what happens if the probability of Walmart doing something and the probability of Target doing something? So look up at the top purple teardrop point, right? This joint probability model, we have probability weighted averages and cross products of those random variables deviations. So that should make perfect sense. So let's work through an example here. You ready? What we're doing is we're going to look at the return on stock A and the return on stock B. But instead of just saying, like we did in those previous examples, stock A did this and stock B did that, we're going to base our expectations on two different scenarios. This is a little bit like what we did with that decision tree in the previous learning module. Not identical, but look at what we have here. If economic growth is going to be less than 44%, which has a 40% probability, well then stock A and stock B will do that, 2, 3, and 6, 5, right? But if economic growth is greater than 4%, which has a 60% chance of occurring, then we're going to get 8% out of A and only 3% out of B. So you should be looking at this. You should be saying, wait a minute. Look, if A goes from 2 to 3 to 8 with less than 4 and more than 4, well, that makes sense, right? We're going to have economic growth. We ought to get more of a return. But B, it goes from 6.5 down to 3. Oh my gosh. So what is this correlation coefficient? What is this covariance going to be? All right, what is the covariance between the return of stock A and stock B? What we need to do is we need to incorporate those returns and their means and this joint probability. All right, so here we go. First thing we need to do is what you would just expect. Let's compute the expected return on A and B. This is super easy. 40% of 23, 60% of 8. That gets us the 572 and the 440. Everybody agree with that? That should be no problem. But now what we need to do is probably put together a little bit of a matrix. And this is done for us right here. So we've got the two scenarios down the left-hand column. Deviations of stock A returns. So what do we have? We know, let me just go back here. We've got 2.3 and 6.5. So that's going to be our first part. So we're going to subtract out the mean. 2.3 minus 5.72. 8 minus 5.72. We do the same thing with B. 6.5 minus 44, 3 minus 44. And so what we're going to do is we're going to take the product of those deviations. So whatever those two columns are, multiply them. You get a minus 7 and a minus 3. Multiply that by the probability, right? So here's this joint probability, 40 and 60. And then you get a minus 4.79. So what did I say back here? It surely looked to us initially that stock A and stock B were going to have a negative covariance and then a negative correlation coefficient. And there it is, covariance of minus 4.79. Now, I want to say a couple of things about correlation and covariance and causation. I bet you read about this if you're regular readers of the Wall Street Journal, and I'm going to go ahead and wag my finger at you. You should be regular readers. You should be daily readers of the Wall Street Journal. That just because two variables are highly correlated does not mean that one causes the other. Let me repeat that. Causation does not result from correlation. That's a super important concept that has applications for all of our regular lifetimes. All right, so what if two random variables, x and y, are independent? Well, then, of course, what we can do is we can say the probability of x and y is equal to the probability of x times the probability of y. But if they are uncorrelated random variables, then what we need to do is take the product of their expected values. So all we're doing is kind of applying probability theory above to the expected values. So that's a simple little slide right there. Let's move on to the last and only third LOS of this learning module. Now, when we have portfolios, what are we interested in? Let's suppose we have a client. A client comes to us and says, hey, we need 10% during the course of the year. So we put together a portfolio and we say, look, this portfolio we expect it to have a 10% return during the next year. Therefore, it will satisfy your return objective. Well, we need to worry about risk. So, of course, we're going to calculate the standard deviation of that portfolio. But let's try to evaluate and let's try to identify some other kinds of risk. And boy, here's a picture of a normal distribution. You can imagine what shortfall risk is. There it is on the left-hand column. What does that mean? It's the probability that a portfolio will not get that 10% or whatever that minimum rate of return that was set by the investor. In other words, if a client sends us $100,000 and says he or she needs 10%, that means at the end of the year, we need to generate $10,000, right? 10% out of that $100. Well, what is shortfall risk? Shortfall risk is at the end of the year, we show up at the client's front door and we say, here's your $8,000. We're really, really sorry. Well, how do we measure that? All right, so this is called shortfall risk. Make sure you understand that it is a downside risk. This is very different than standard deviation. Standard deviation went on both sides of the mean, both sides of the expected value. Shortfall risk is a downside risk. We're only looking at the left tail of the distribution. And this is going to set us up beautifully for other material that we cover in levels 1 and 2 and 3. In particular, one called value at risk. We'll do that some other day. So we identify the shortfall risk, we identify the standard deviation. How can we use this stuff to help us make decisions? So we have this safety first ratio. There it is in the beige box. What we're going to do is we're going to take the expected return on the portfolio, which we've calculated, right? We're going to subtract out the R sub L, which is some kind of a desired return level. That's the 10% that our client came to us. So the expected return in the portfolio minus that, think of it as a minimum level of acceptable return, the desired, the aspired, is some return that the client says to us, look, man, it would be awesome if you could get this number. And then we're going to, oh my gosh, we're dividing by standard deviation. So we're standardizing that numerator. So notice that we have return in the numerator and standard deviation in the denominator. And so this is the safety first ratio. And look at that second teardrop point. And this is a super important one. We don't know a whole lot about this just yet, but you will in the next handful of videos. If returns are normally distributed, just assume, here, let me go back here. There's a picture of the normal distribution. So if the returns are normally distributed, then the optimal portfolio is the one with the highest safety first ratio. That should make perfect sense, right? We want lots of numerator and just a little bit of the denominator. So the optimal one is the highest safety first ratio. And then what you can do is look at the second beige box down there. You can go ahead and compute the probability that portfolio return is going to be less than that desired return. And so imagine drawing a line down from the normal distribution to the horizontal axis and then shading that area in down there. The area under the curve is a probability, so that shaded area would be the probability that we're going to let our client down. Let's take a quick example here in finishing up. Let's see, minimum threshold return. There's another way of saying that, 3%. We need to pick among portfolio A, B, and C. There's the expected returns, and there are the standard deviations. So the optimal portfolio, we're going to use that safety first ratio. So there are the super simple calculations. So there we got, what do we have? 13, 35, and 68. Oh, there we go. We have it bolded. So the optimal portfolio that will maximize the safety first ratio is portfolio C. Now, there are lots of other ways to evaluate an optimal portfolio, but what the Institute would have to do in the question stem is say something like, hey, using the safety first ratio, which one of these is the best portfolio for this particular client? That takes us through our 3 learning outcome statements. I'll just repeat myself. We've done a bunch of this stuff before, but what we've done now is we have added it to a portfolio context. So I want you to go ahead and take 5 minutes and look at the singular problem at the end of this learning module and work through it. So hey, thanks for watching. I had super fun here. Have a great day and good luck studying.